Intermittent fasting, IF, has generated tremendous interest over the past decade, fueled in large part by compelling results from animal studies. Rodent models, in particular, have demonstrated dramatic improvements in lifespan, metabolic efficiency, insulin sensitivity, and markers of cardiovascular and neurological health. In many experiments, mice and rats subjected to time-restricted feeding or alternate-day fasting exhibited reduced fat mass, improved glucose regulation, lower inflammation, and even delayed aging at the cellular level. These findings have understandably contributed to high expectations that similar effects would occur in humans. However, translating results from animal studies to human health requires careful consideration, as the physiological, behavioral, and environmental differences between species can significantly influence outcomes. While intermittent fasting does appear to confer benefits in humans, the magnitude and consistency of these effects are often more modest than what is observed in controlled animal experiments, and understanding why can provide valuable insights for designing effective human interventions. One of the main reasons benefits seen in rodents do not always translate to humans is the controlled nature of laboratory studies. In animal experiments, researchers regulate feeding times, calorie intake, diet composition, temperature, activity, and even light exposure, creating near-perfect conditions to study metabolic responses. Rodents often receive a high-calorie diet within strict fasting windows, and researchers can ensure complete adherence without the behavioral and social challenges humans face. In contrast, human trials are influenced by diverse lifestyle factors. Work schedules, social obligations, sleep patterns, meal composition, and adherence all vary, introducing variability in outcomes. Even when human participants follow prescribed time-restricted eating windows, compliance can fluctuate, and late-night snacking or deviations in diet quality can dampen the metabolic benefits observed in animals. Metabolic rate and energy balance also differ fundamentally between species. Rodents have a higher basal metabolic rate, shorter lifespans, and rapid cellular turnover, which magnifies the impact of fasting interventions over relatively short periods. Fasting periods that are proportionally longer for a mouse can trigger dramatic shifts in energy utilization, autophagy, and hormone regulation. In humans, with slower metabolism and longer lifespans, comparable fasting periods produce more subtle effects that require weeks or months to become measurable. This explains why benefits such as significant weight loss, enhanced insulin sensitivity, or cardiovascular improvements, while present in human studies, are often smaller in magnitude and slower to manifest compared to rodent data. Hormonal regulation and circadian alignment also differ between species. Rodents are nocturnal, meaning their natural activity and feeding cycles are opposite to humans. Time-restricted feeding in rodents is often aligned with their active nighttime period, which coincides with peak metabolism. Translating this approach to humans is not straightforward. Fasting or feeding windows that do not align with human circadian rhythms may blunt potential benefits. Early eating windows in humans, which align with morning insulin sensitivity and thermogenesis, show more consistent improvements in glucose control and fat oxidation than late-night eating, highlighting the importance of timing in addition to fasting duration. Furthermore, human physiology introduces additional complexity in terms of genetic diversity, lifestyle, and pre-existing health conditions. In rodents, homogeneous genetic strains allow researchers to isolate the effects of fasting without confounding variables, whereas humans vary in insulin sensitivity, lipid metabolism, chronotype, and propensity for weight gain. Some individuals respond strongly to time-restricted eating, experiencing improved glucose regulation, reduced inflammation, and enhanced fat loss, while others show modest or negligible changes, even when caloric intake and meal timing are similar. This variability underscores the need for personalized approaches rather than assuming that protocols effective in animals will automatically produce uniform results in humans. Past human studies also face limitations that can obscure the translation of benefits from animal models. Many trials are short-term, often lasting only a few weeks, which may be insufficient to capture long-term metabolic or cardiovascular improvements. Sample sizes are frequently small, and interventions vary widely in fasting duration, timing, and diet quality, making direct comparisons challenging. Additionally, many studies rely on self-reported adherence or food logs, which introduce error and reduce precision compared to the tightly controlled conditions in rodent experiments. Despite these limitations, The growing body of human research consistently demonstrates that time-restricted eating, alternate day fasting, and other intermittent fasting protocols can improve body composition, stabilize blood sugar, reduce blood pressure, and lower markers of inflammation, even if the effects are subtler than in laboratory animals. Importantly, the contrast between animal and human studies does not diminish the value of intermittent fasting. Rather, it highlights the complexity of human metabolism and the need for realistic expectations and individualized approaches. Human trials show that fasting works best when integrated with nutrient-dense meals, regular physical activity, consistent sleep, and circadian-aligned eating schedules. Personalized timing, tailored macronutrient composition, and gradual adaptation to fasting windows maximize adherence and metabolic benefits. Far from being a limitation, this variability offers opportunities to refine fasting strategies, leveraging the lessons learned from animal models while accommodating human physiology and lifestyle realities. In conclusion, animal studies provide powerful mechanistic insights into the effects of intermittent fasting, revealing how fasting triggers fat oxidation, enhances insulin sensitivity, reduces inflammation, and promotes cellular repair. Translating these benefits to humans, however, is influenced by lifestyle, circadian rhythms, genetic diversity, and behavioral factors, resulting in more modest but still meaningful improvements in metabolism, cardiovascular health, and overall well-being. Understanding these nuances underscores the importance of personalized, flexible approaches to intermittent fasting, allowing individuals to harness its science-backed advantages in a sustainable and positive way. While humans may not experience the dramatic outcomes observed in rodent models, the cumulative evidence supports TRE and other fasting protocols as effective tools for enhancing metabolic efficiency, improving energy regulation, and promoting long-term health.